Hi everyone, welcome to a new video. Today I would like to showcase something very powerful for basically Git versioning any custom machine learning model using the HuggingFace hub. So as you may know, the HuggingFace hub is this central place where a lot of machine learning models can be found. So for example, here on the left you can see all kinds of different tasks by domain. So you have, for example, the computer vision domain. So you can, for example, find machine learning models that can do depth estimation. You can find models that can do video classification. Of course, there are a lot of natural language processing models available on the HuggingFace hub as well. We now also have multi-model models, which combine several modalities. So for example, Blip is a very nice new vision language model. So it combines both the image and the language modalities to do tasks like image captioning. So you can also easily filter out models on the hub by selecting an appropriate tag. But one thing that a lot of people don't know is that actually the HuggingFace hub is not only meant to host models that are available in the HuggingFace Transformers library, because of course the most downloaded models that you see here, like Bird Base Encased, GPT-2, Clip, and so on, Layout LM v3, these are all models that are available in the HuggingFace Transformers library. But the HuggingFace hub can actually be used to host and Git version any custom PyTorch model or any custom Keras TensorFlow model. And this is what I would like to showcase in the video of today. So the thing we're gonna use today is available in what we call the hub client library. So the hub client library, or the HuggingFace hub library, is like it's a Python library that is sort of a Python interface to the hub. So you can use the HuggingFace hub library to programmatically interact with the HuggingFace hub. So you can use it to, for example, download any file from the hub. So for example, we provide a HuggingFace hub download function, and then you can simply specify a certain repository ID, certain file name, and it will load that file from the hub. You can, of course, also upload files to the hub. For example, using the upload file method and so on. But the thing I would like to showcase today is called the PyTorchModelHubMixin class. And this is this very powerful class that basically allows you to host, well, basically push to the hub any custom PyTorch model and then load it back again using the from pre-train method. So it's illustrated here, the basic usage. So yeah, in PyTorch you typically define your custom model by inheriting from the in.module class. And so the thing you need to do here is you also need to inherit from the PyTorchModelHubMixin class, which is available in the HuggingFace hub library. And then you automatically inherit methods like save pre-trained, push to hub, and loading it back again using from pre-trained. So that's something I would like to showcase today. So for that, I'm going to create a new notebook. And I'm just going to take the basic PyTorch tutorial, which I think is done on the imnist dataset for training an image classifier. And so I'm gonna copy most of the stuff that they are using here in this demo. But I'm gonna make sure that our custom neural network is inheriting from this PyTorch ModelHubMixin class. Now I'm gonna first install a bunch of libraries. I'm gonna use the datasets library, because also the datasets library is very tightly coupled to the hub. So here you can also find a lot of datasets. For example, by task, like you can find visual question answering datasets and so on. So I'm gonna install the datasets library to load a particular dataset for demo purposes from the hub. And I'm gonna also install the HuggingFace hub library, but I'm gonna install it straight from source because it includes some brand new features that are not yet available in a PyPy release. So I'm gonna just install it straight from source, from GitHub. So I'm gonna call this notebook Git-version any custom PyTorch model using PyTorchModelHubMixin. And note the thing I'm gonna illustrate today, it actually also exists for Keras as well as fast AI models. So for example, if you have your own Keras TensorFlow model, then you can inherit from the Keras model hub mixin class, and this allows you to also do things like save pre-trained, push to hub from pre-trained. There's also a from pre-trained Keras method and push to hub Keras method, which also allow you to do the same thing without having to define the model class every time you use it. So let me call this section the setup environment section. Then let's say we want to load a particular data set for doing, so I'm gonna call this define model. Let's load one particular image classification dataset, so that's very easily doable. You just need to do from datasets import load dataset, and then you can specify a particular dataset from the HuggingFace hub. So in this case, let's check a image classification dataset. So of course CFAR10, Fashion Imnist are pretty known datasets, ImageNet of course. Let me load the Beans dataset here, which is a dataset that, well, the goal is to classify whether a bean leaf is healthy or not. I think this dataset has 2 or 3 classes, and so the goal for the model is to determine whether or not the leaves are healthy or not. So it consists of 3 splits here. I'm just gonna take the first example. So I'm gonna take the first training example, and the nice thing is that you can directly visualize it in a notebook, as the image feature is based on pillow. So let's also check the corresponding label. So the features here, let me check the features. So we have 3 features here: image, which is of type image; labels, which is of type class labels. So we have 3 classes here: angular, leaf spot, bean, rust, and healthy. So if we check the label here for this particular image, it maps to 0. So this means it's of type angular leaf spot. So I'm gonna create a ID to label mapping here. So let's call this features, and then we can create an ID to label dictionary that simply will map these integers to their corresponding class names. Okay, nope, this is not correct. It should be it should be like this. Okay, so now we have a dictionary that maps IDs to their labels. So then we can do ID to label and provide. So now it maps to the appropriate class. Of course, you may wonder, like, let's say you have your own images and their own classes. How can I load it into a HuggingFace dataset object? Well, for that we provide the image folder feature in the HuggingFace datasets library. So let's say you have a folder with your dog images and your cat images. Then you can simply use this image folder feature. You can provide the path to your images, and it will automatically create a HuggingFace dataset object for you. And it even supports remote files. So let's say you don't have a folder with your local folder with your images. Could also be that you have like a remote zip file stored somewhere. Then you can also provide it to this image folder builder, and it will automatically turn it into a HuggingFace dataset. But for that, I refer to this create an image dataset guide in the documentation of HuggingFace datasets. Alright, so we have our dataset. Cool. The next step is then to create a PyTorch dataset, because that's like the standard way of preparing data for a PyTorch model. So for that, I'm gonna wait, create a custom PyTorch dataset. Yeah, this one. And then let me just copy over this class here. So basically, so let's call it custom dataset. To define a PyTorch dataset, you need to inherit from one particular class, which is in the torch.utils.data package. So it's the dataset class. Let's call it an image classification dataset. And then you can basically define some custom attributes. So here I'm just gonna make this PyTorch dataset take 2 arguments, which are the dataset itself and then some image transformations. And then you need to implement 2 additional methods, which is the length method, which will return the length of the dataset. So this is just length of self.dataset, and then the get item method, which will return one particular item, one particular example of the dataset. So for that, we first going to get the example. So item equals self.dataset at that particular index, and then, well, we can get the image by getting the image. Well, I'm gonna require that we provide an image transformation. And then we can provide it to the image transformation, and then we simply return it along with the label. So note that it was called labels in the dataset. Like this. Of course, chances that this is going to work from the first time is small. So let's say we create a train dataset by calling this, by instantiating this custom dataset, and then we provide the training split of our dataset together with some image transformations. So to provide some image transformations, you can use the TorchVision library. So the transforms package has some very nice operations for doing, well, for having some image transformations. So the reason we do this is when we want to prepare our images for a neural network, we typically apply some basic transformations on the image, which involve, for example, resizing the image to one particular size, and then normalizing the image such that it is in the 0 to 1 range, for example, or we often normalize the channels using the ImageNet mean and standard deviation. So let me go back to the PyTorch MNIST tutorial. Let's see what kind of tutorial. Yeah, this one. Let's see what kind of transformations they were. Oh, they were using very simple transformations, so just 2 tensor, which will rescale the pixel values. So here we do from TorchVision import transforms, and then we compose several transformations in one chain. So here we call 2 tensor. So 2 tensor in TorchVision will simply rescale the pixel values. So it will convert a pillow image or an NumPy array to a tensor, and it will make sure that the values go from the range 0 to 255 to the range of between 0 and 1. So that's what we need. And then we can do a normalize operation, for example, using this mean and standard deviation. And then we call the we provide the transform to our training dataset, and let's see whether our first example of the training dataset is prepared correctly. So in this case, it returns 2 things. It returns the prepared image, which, well, it's now having values between 0 and 1, so it's not really interpretable anymore. We would have to denormalize it to get back our image. And then this is the corresponding label. So that looks fine. So the next step then in PyTorch is to create a corresponding PyTorch data loader. Because neural networks, they're always trained not on one example at a time. We typically provide batches of examples because these models are optimized using stochastic gradient descent. And so this is done on batches of data rather than individual examples. So for that we need to inherit, import again from the same package torch.utilsData, and then we say we want to import the data loader class, and then let's create a data loader as follows. So we provide our training data set. We specify a certain batch size. So we, for example, want to get batches of size 4, and we say shuffle equals true, because typically we want to shuffle all the training examples to create random batches. And then you can get the first batch from your training data loader as follows. So you can loop over it, because a training data loader is basically a generator class in Python. And a generator is basically a iterator that will only provide the data when you loop over it. And this is efficient because this way the data will only be loaded into your RAM when you need it. So I'm gonna loop over our training data loader to get the next batch. So let's see whether this works or whether we get some error. So in this case that seems to work fine, and we get, let's see what we got. So we have a list here. Let's see what the first item is and what the shape is. So in this case, the first item returns a PyTorch sensor of shape, batch size, number of channels, height, and width. So in case of the beans data sets, I think all the images have the same resolution already, which is 500 by 500 images resolution in terms of height and width. So we don't actually need to resize anything here. Well, assuming that we're training on images of size 500 by 500, which is a relatively high resolution. And we have 3 color channels, and our batch size is 4. And then we can print out the corresponding labels. So in this case, for example, we have 2 images of class 0 and 2 of class 1. Okay, so that's fine. So now comes this very powerful PyTorch model hub mixing class. For that we need to just do from HuggingFace hub import PyTorch model hub mixin, and then we can inherit. So let's say this is our custom neural network. So we inherit both from the in.module class as well as the PyTorch model hub mixin, and then we instantiate our custom neural network. Well, here we see that the number of output neurons of our neural network is set to 10, but here we have 3 classes, so let's set it to 3. And let's see whether this works. So before training our model, a good sanity check is to just do a single forward pass. So we had already our batch here from our training data loader. Let's see whether we can just do the following. Net and then batch. Well, it only takes x, with x being the pixel values. So we just need to provide the first element of our batch here. Let's see whether this works. It seems to, well, yeah, this is because I just took this custom neural network from this tutorial here. So of course, chances that this is going to work on our resolution of 500 by 500 is relatively small. Yeah, there's an issue with the first fully connected layer. I think I'm just gonna fix this now. Yeah, now this works. Yeah, this is just hard-coded for the moment, but it's just for illustration purposes, to make it work on images of size 500 by 500. But now we get our logits, because that's what the model returns back. And so these logits are like the unnormalized scores of our neural network. So these logits, they have a shape of batch size number of labels, and basically the neural network is returning for every single example in our batch a score for each of the 3 classes. So if you want to get the scores for the first example in our batch, we need to do the following. And this returns, for example, but note that these scores, these logits, they are not normalized. So they don't count up to 1, for example. They don't sum up to 1. They are just unnormalized. We would have to apply a softmax, for example, on them to get like a probability distribution that will sum up to 1. But in this case, the highest value is this one, 0.14. So we would say that our neural network thinks that this first image, for example, has class number 3, which in this case means healthy, if I remember correctly. Yeah, well, class 2 if we start counting from 0. Okay, so we've done this sanity check, then I think it's time to train the model. But so, as we inherited here from this PyTorchModelHubMixin class, we can already do the following. So we can simply do net.push to hub, and then we can specify, for example, let's call it custom neural network. So this is not going to work from the first time, because we need to first authenticate with the HuggingFace hub. So for that you can do the following: HuggingFace CLI login. And then you can simply provide your authentication token to it. And then you can also optionally store it as a Git credential, and then you can do net.push to hub. And this will automatically already push your custom PyTorch model to the HuggingFace hub, and it will be Git versioned. So in this case we get a URL back. Well, actually, if we just serve now to the HuggingFace hub website, you can see that it has uploaded this custom neural network. And if you click on the files and versions tab, you can see that the weights now are stored here. And so this is all versioned using Git LFS. So LFS stands for large file storage, because yeah, we have relatively large files which are not stored or hosted, for example, on GitHub. But here, yeah, we can host them using Git LFS. And so as you can see, we now have 2 commits, and we can always refer back to one of these commits. We can also optionally create a model card, which is just a readme. So you can, for example, say custom neural network. This is a custom neural network that will be trained on the beans dataset. And you can, for example, also include a link to it. Well, actually, you can link automatically here by providing a tag, and then it will also automatically link it, actually. So let me also provide a link in the in the model card. And now it looks like this. So of course you can expand this and document everything you want, and so now it's automatically linked with this beans dataset. All right. So then we can also load it back again. So reloaded model would simply be, and then custom neural network, but from pre-trained, and then we specify our repository ID, and then it will reload it. But of course, yeah, we haven't trained anything here yet. These weights are just randomly initialized, so of course we would first need to train our model on a dataset before we can actually use it. So that's what I'm going to do in the next step. So for that, I'm going to go back to the tutorial here. I'm going to just copy this over. So what is done typically in PyTorch is we define a loss function. So in this case, we are using the regular cross entropy loss, which is used for image classification. And then we define an optimizer. I'm going to use the Adam optimizer here. We provide the parameters which we would like to optimize over a neural network. We specify learning rates. I typically use 5e-5, which oftentimes works well for me. Let's hope it does here as well. And then the next, or the final step, is defining a training loop. So for that, we are just gonna iterate over our data. So let's say we trained for like 5 epochs. So here we loop over our training data loader, getting the inputs. Well, our batches of our training data loader are actually lists, if I remember correctly. Sorry, they're actually lists. Yeah, so I'm gonna do the following to turn them into a tuple. We zero gradient. Well, this means that we don't want to accumulate gradients. We simply zero grad them, because otherwise the gradients of the parameters would be accumulated. Then we do a forward pass here using our inputs. Well, actually, I'm gonna do it a bit differently here. I'm just gonna say the pixel values are batch 0, so the 0 index. We forward them to our neural network, and then the labels are batch 1, and then we compute the loss here. We do a backwards, so this will compute the gradients, and then we do optimizer.step. I'm also gonna inherit here from the TQDM, not sure how to pronounce this, library, to basically have a progress bar to see how fast we're going over the data. And then, yeah, they also define a running loss, which will allow us to print out the loss every, well, let's say maybe one every 50 mini batches, maybe. And so the cool thing is also that, for example, let's say we want to push the model to the hub after every epoch. We can simply do that as follows: pushing model to the hub. So we can simply do model.push to hub. We can specify a repository ID. So in this case, I'm gonna specify this repository ID, and then we can also have a commit message. So in this case, let's say training in progress epoch, and then we can, for example, use an formatted if string. So this will also allow us to basically push the model to the hub after every epoch, and then we can also reload it back again for every epoch that we would like. So let's see whether this works. And it says that it has an issue here when calculating loss. Let me print out the shape of the labels. So they are of shape 4-1. Let's see, the model outputs logits of shape, batch size, number of labels, and then we have the labels. Oh yeah, these I think we should just squeeze them. Because we don't need to have two-dimensional labels. So now, yeah, we do have a progress bar because we are training the model. Normally we will also print out the loss after every 50 millibatches. So currently we're at millibatch 17. So yeah, let's see whether this works, and then I can also illustrate the push to hub functionality. So by pushing the model to the hub after every epoch, and this will then just show up as a new commit here. So it will simply overwrite this PyTorchModel.bin file. So yeah, it's printing out a loss. Well, actually a good sanity check that we also didn't do here, that I got from this very nice blog post from Andrej Karpathy, a recipe for training neural networks, is computing the initial loss. I'm not sure if it's included in this. Yeah, verify loss at initialization. So for example, when using the cross entropy loss for classification problems, then your initial loss should always be around minus the log of 1 divided by the number of classes. And the reason that it is like this is because at the beginning of training, your weights of your model are randomly initialized, so the model will not know anything, so it will just output a uniform distribution among all the possible classes. And the cross entropy loss is always defined as minus the log of the probability of the model for the correct class. But so as the probability for the correct class at the beginning of training is completely random and uniform, it will just be equal to 1 divided by the number of classes. So basically the initial loss for our model should be around 1.09, and it looks like that was the case here as well. So now it's going down because the model is learning. But this is also a good sanity check, which you can always use when you use the cross entropy loss. But of course, yeah, it would be different for other losses like the L2 regression loss or Huber loss and so on. But yeah, so the model seems to learn at least. Well, actually, just for demo purposes. So I'm not too sure whether this custom neural network here is like very optimized, but the main thing I wanted to showcase in this video is this PyTorchModelHubMixin class, which allows you to basically just host and then Git-version any custom PyTorch model. And so also note that you can simply set it to private. So for example, let's say you are using the private hub, the private HuggingFace hub. Then you can, for example, only share it with your colleagues or people that you are part of the same organization. For example, you can click here on create an organization, and then it allows you to create your own organization, for example, for your company with all your machine learning engineers, and then it allows you to basically have several models part of one organization. For example, Facebook has all these models available, but yeah, these are all public models. But yeah, with this setting here, you can set it to private, and then this allows you to only share models with colleagues, for example, that are part of the same organization. So that's an additional functionality. And so yeah, there's also a community tab which allows you to discuss things for a certain model. So basically, if you go, for example, to the bird Bayesian case, I'm pretty sure there will be a bunch of discussions. So these are a bit like GitHub issues where people can discuss things related to machine learning model. And there's also the possibility to open pull requests if you, for example, want to modify anything related to the model itself, to the weights. So let's say you have trained a better model, or whether you just want to improve the model card, for example, or add metrics and so on. So yeah, now we are passed through the first epoch. So here we have pushed to the hub. So let's go back to our model. And as you can see here, now we have an additional commit. So training in progress, epoch 0. And so this is very nice because now we are training our model. The loss keeps improving, well, keeps going down. And yeah, we can simply version our model using this very simple PyTorchModelHubMixin class, of which you can find the documentation just in the hub client libraries documentation. So yeah, maybe after this second epoch here, I'm gonna just showcase reloading and performing inference on an image. But yeah, this is like the basic idea. And so note that you can do exactly the same using Keras. Alright, so I'm just gonna stop training here because we've just pushed again to the hub. So let's go back to our model on the hub. So now we have an additional commit here, training in progress epoch 1. So for example, now we can simply reload it. So reload and perform inference. So for that we can simply reload model. Dot from pre-trained. So let's say we want to specify this one, and we want to specify, well, by default it will just fetch the latest commit. But one thing you can also do is just specify the revision argument here, and then you can specify, for example, I want to get this particular revision. This is also possible. But so yeah, let's just use here the best model, and then you can simply use it and do inference. So in this case, let's say we have our training data set. So this particular example image, which I think is still loaded into RAM. So the corresponding ground truth class here was 0, which means angular relief spot. So let's prepare the image for the model. So for that, I'm just going to call the transform on our image. Like this. And then we are going to do a forward pass. So in PyTorch, this is done most efficiently by using the with torch.nograd context manager. So just model pixel values. We need to unsqueeze them to add the batch dimension. Sorry, this is called reloaded model. So we get our logits out, which are of shape batch size number of classes. So here we only have a batch size of 1 because we only have a single image. We have 3 classes. So let's just call argmax here on the last dimension to get the prediction from the model. So in this case it predicts the class 1, which is correct because the ground truth label was also it predicts 0, and it also corresponds to the ground truth class of 0. And we can also, let's say you want to get the probabilities. So as I said, the logits are just unnormalized scores that the model gives to each of the classes. If you want to turn them into probabilities, you need to use softmax and PyTorch. So for that you can either use n.softmax. Let's use that here. So probabilities. For that we do n.softmax. Oh yeah, this is okay. Yeah, if you define it as a PyTorch module, then you can do the following: probabilities equals module logits. And so this in this particular case, for example, we have a 57% probability that the model thinks this particular example is of class 0. So yeah, that was about it. So in this video I've showcased a bit the power of the HuggingFace hub for hosting and Git versioning any custom PyTorch model using the Mixin class. I hope you enjoyed it and that you learned something, and see you in the next video. Bye bye.